everyone, welcome back to my channel, and today I want to talk about Pipecat frames. So today's talk will be all about Pipecat frames, specifically system frames, and in the end I also want to discuss interruption, how interruption works in voice AI, because interruption is a big part, and I feel it's important to know underneath how interruption works in voice AI. So yeah, let's get right into it. So today's goal, as I said, we are gonna discuss about frames, why Pipecat uses them, how frames move. We are gonna discuss about downstream, upstream, broadcast, what each of them is, and also we have discussed already about pipeline task. Today I'm gonna also discuss about pipeline instance. So it's kind of like a mental model. um, uh, we won't be writing this in the code, but I wanted to talk a bit about it so that we can understand exactly about pipeline task, and how frames work inside the pipeline task. And then we are gonna come to system frames, why they exist, what system frames are, and who emits them, who receives, what happens for each system frame, and how interruption works. This is gonna be a lot in detail with some diagrams. So yeah, so let's get started. So first of all, this one sentence I want you to keep in mind, because this single sentence explains almost the entire architecture. Nothing in Pipecat directly calls anything else. No processor says, "Hey, call the LLM now." Instead, it emits a frame. So those frames move, get handled, transformed, or cancelled. If you ever feel lost, come back to this sentence. Pipecat is an event-driven system where everything that happens is represented as a frame flowing through processors. So no direct calls, no shared global state, only frames plus rule. So now coming to what exactly is a frame, you can think of a frame as a fact about the world. It's a structured message, like whenever we have whenever something happened, an audio arrived, a user spoke, an error occurred, that becomes a frame. So frames are not command, they are events. So the metadata inside is intentionally flexible, like it lets processor communicate without tight coupling. So think of frame as a timeline of reality flowing through the system. So we have different types of frame, like input audio raw frame, user started speaking frame, cancel frame. So these are the different examples, and every frame has these properties. So we have this metadata which is flexible, and it lets processor communicate without tight coupling. So yeah, so now why frames instead of function calls? So function calls assume linear control. Real-time systems are not linear. Problems in real AI system, like multiple thing happen at once, like interruptions, cancellations, partial failures, user interrupts, audio overlaps, model fail. So yeah. Now frames make interruptions normal, not exceptional. So cancellation becomes just another event, not a special case. So this is why Pipecat scales from simple demos to production voice agents. Uh, so how frame do this is by making state changes explicit and allowing cancellation at any time using frames. uh, Keep processor loosely coupled, and enabling priority based processing. So yeah, so this is how frames help us. And coming to the processor and pipeline, so this is something that we have already discussed in the previous video. So a pipeline is a chain of processors. So we have some input, like transport, then audio is received via WebRTC, and then using transport, we send it to STT, then LLM, then TTS, then some speaker audio output. So each processor only knows about the frame it received and frame it emits. Processor don't know who is upstream or downstream, just next and previous. So that's why we have like what is the next and what is the previous one. And this is deliberate. It keeps processor reusable and testable. Everything interesting happens at the frame boundaries. So so yeah, so processor just receive the frame and they emit new frame, so via this process frame and push frame. And we are gonna come to direction in a bit. So pipeline, uh, before discussing everything about frame, I wanted to uh, make one distinction about pipeline task and pipeline instance. So in the previous video we have already seen pipeline task and pipeline runner. So now this pipeline instance is something we did not cover in the previous video because this is not something related to code, but I wanted to take some analogy and discuss over here. So I'm just gonna first give a analogy like in case of API server, uh, you can think of what are the different pieces involved. So whenever you are writing the source code, this is the code that you will be running on some server, and some server is processing that user request. So one request that we receive, and that is received on the server, and our code is running that, right? So in terms of Pipecat, the equivalent would be like the source code would be the pipeline definition, like what is the pipeline consisting of, like STT, LLM, TTS, and in between whatever it is. And what are when that pipeline is running, that is like a pipeline instance is the running service, like models loaded, processors wired, and all of that. And pipeline task is a session, a phone call, a user interaction. So whenever a user is calling, then we create one pipeline task. So user is calling pipeline task, so user A, we create one pipeline task 1. Then user B is calling, so we are creating one pipeline task 2. And then user C is calling, we are creating another pipeline task. So one instance can handle many tasks at once. So and inside these each of these pipeline tasks, we process the frame. So the frame that is being processed for this user are going to be different for this user. Basically this pipeline task will have even they might look same. Like for example, if we have start frame or end frame, or end task frame actually. So let's say whatever frame we have, it might look the same, but it is actually different for each of these pipeline tasks. And pipeline instance is like a running service of that pipeline. So now the thing is like I'm gonna come back to it in a bit, but wanted to make this distinction clear. So whenever we define the pipeline, we actually create a task and then run the pipeline using the pipeline runner. So this pipeline instance is the running service of that pipeline task. We can have like different task. So yeah, and now coming to task, like task are how Pipecat handles multi-user system safely. Each task has its own frame flow, like interruption state and life cycle. um, and system frames almost always operate inside a task. So this is why one user interrupting does not affect another user. So that's why we have these tasks. Now um, we have like three different types of frame. So the we have like a system frame, we have data frame, and then control frame. So there are three types of frame, and out of which we have a priority defined. So we have a system frame with highest priority, like this is the high priority, and then Data frame and control frame are low priority. Now, uh, why is that? Um, hierarchy explains uh, uh, hierarchy explains priority and not behavior. Like system frame is about urgency, not semantics, and data frame are kind of normal data payloads, and control frame manage the flow, not meaning. So if you remember nothing else, priority comes from uh, from the base class, depending on the type of frame, we have the priority. So system frame is the highest priority, and data frame and control frame are low priority. And priority is determined by the frame type, not by frame content. So based on this frame type, we define if it is a system frame, this is a high priority, otherwise it's a low priority. Now now uh, why we have this priority? Because sometimes you would want certain frames to process at a faster rate, in respective of other frames. So that's why we created a priority for these frames. Now coming to the direction, so frame direction, this is very important. So direction answers where is the information going. So we have generally two direction, like downstream is the happy path, like input to output, and upstream is like a control, like whenever we want to stop, cancel, error, or interrupt, we have to go upstream in certain cases. And you can't reason about frames without knowing direction. Same frame type, different direction, totally different meaning. So we have to understand, like whenever we will be dealing with different frames, they might be moving downstream, they might be moving upstream. So downstream is the normal flow, like you can see transport, STT, LLM, TTS, and speaker, and upstream is the opposite one. Yeah. So now, talking about broadcast. Broadcast is about sending both direction. Mm, Broadcast is often misunderstood. It does not magically send to everyone at once. uh, it sends two frame, one downstream and one upstream. um, and every processor in those paths will see it. So generally regular push frame is we, for let's say LLM is sending it, so we send it upstream and then we also send it downstream. So this is like we are broadcasting it downstream and upstream. So this is about broadcast, and you can think about it as announcement to everyone, push from like message to the next and previous. Okay, now talking about queue inside each processor, this is something I want to take uh, a bit. Uh, I want to spend some time on this, because we have to understand, there are two types of queues involved. So uh, whenever we talk about how the frames are processed inside a processor, so each frame processor instance, we have something like a input queue. So all the frames that are coming to a processor gets queued in this input queue, and this is kind of a priority queue. Now we have this input uh, frame task handler, which sees all of these frames, and based on the priority of these frames, it decides whether we need to process it immediately or put it into another queue. So we basically check if the priority is higher, like if this is a system frame. So as we talked, system frame has the highest priority, like a system frame has the highest priority. So we just check if it is a system frame, we process it immediately. But if it is not a system frame, then we put it in the process queue, and then another task handler, process frame task handler, processes these frames in order, and then we push it to the next or previous processor based on the direction. So this is how two separate queues work inside a processor, and how system how when the frames are being processed inside a processor, how they are handled inside the processor, and based on the system frame, like they are processed immediately, and other types of frames are processed at regular on a regular basis. So we have these two types of queue: input queue and process queue, and based on the priority we decide. High priority is for system frames, and process queue is a regular FIFO queue that holds non-system frames, and it can be paused or resumed and drained during interruption. So we are gonna talk about this, but yeah. And we also have two different task handler, like it processes from the input queue and handles system frame immediately, and put frames apart from system frame into process queue, and then process frame task processes from process queue in order. Yeah. So this is the heart of how priority works. And now, why high priority? Like high priority means handle this now. It does not change direction. It does not imply broadcast. Priority only affects queue order. This separation is what keeps the system predictable. So yeah. Um, Now there is something also known as uninterruptible frame. So there are two types of frame: function called result frame and function called in progress frame, which are uninterruptible. So sometimes during interruption we want certain frames which are uninterruptible, um, and these are two of these frame: function called result frame and function called in progress. Like critical, whenever any critical operation is in progress, so we can have this frame, and sometime we need to update context, so we can have these frames. Yeah. And the interruption is powerful but dangerous, and some things must finish no matter what. So uninterruptible is an explicit contract, and we kind of use it sparingly and intentionally only. So now this is where we are get started with system frame. So system frame, this is the first frame that we are gonna talk about. So I think I'm gonna decrease the size of it. Yeah, okay. So we are gonna first talk about start frame. So start frame is kind of like the birth of a task. So this is where processors learn how the world works. Like for example, sample rates, metrics, configuration, and all of that. We define it here in the start frame, and every processor should treat it like it's the starting point, and if start frame is wrong, then everything after it is wrong. So it initializes the processor state, pass configuration, sample rates, metric settings, all of that, and it is of definitely we are talking about system frame. So this is of system frame type, and it travels downstream and priority is high. These are the different parameters. So we keep these parameters inside start frame, so as whenever we are starting pipeline task, this start frame goes through each and every processor, and whatever configuration we want to adjust or initialize in those processors, we define it here. uh, so so yeah, store the configuration and initialize the internal state and forward start frame to the next processor. So this is kind of the start point. So why start frame must be first? Like if start frame were late, audio could arrive before sample rate is known. So if we did not, so let's say our sample rate is defined in the start frame, and if they were late, then the model wouldn't know what is the sample rate that we have to process the audio. So audio could arrive before it, and the start frame is late, and now it didn't know what to do. Similarly, LLM couldn't run without the prompt setup and metrics wouldn't be collected. So all of those. So that's why start frame is required so that each processor know, okay, this is the some configuration I require, and so that they can process the next set of frames. uh, as you can see, so based on this start frame, data can flow. So now coming to, there are two different types of error frame which are of system frame type, and they serve a different purpose for our application, for our voice AI agents, which is error frame is recoverable error type. Like this is generally uh, when when we want to control certain things, like we want to recover from error, but fatal error frame is unrecoverable, like we want to shut down or do something. So one thing that you need to remember is they both travel upstream, like, apologies for this, uh, yeah, sorry about that. So uh, you must know that these error frames travel upstream whenever any error occurs. So we want to notify the previous processors, like, hey, this is the error, so we have received the error in TTS, so do something or stop something. So we need to notify the above processors. That's why this error frame is there. Now we have two different error frame. If the error is recoverable, we just send the error frame, but if it is unrecoverable, then we just send that unrecoverable like fatal error frame, so that it forces shutdown. So we have two error frame for that, like error frame and fatal error frame. Then coming to interruption flow, uh, this is something brief we are going to discuss, but we are going to discuss in detail towards the end. But something that you need to know is we have two types of interruption frame. One is interruption frame and one is interruption task frame. So interruption frame is a system frame, and whenever a user starts speaking, like when the bot is running, bot is giving an output, and in between the user is interrupting the bot. User is interrupting. So uh, at that time, interruption frame is processed. So interruption frame is it travels downstream, and we cancel all of those tasks at for different processors, so that when the all of these tasks is cancelled, so that new data can come, new audio can come, and the processors gets ready for the new input. So TTS cancels audio generation, it cancels text generation, it cancels all the different tasks. And because user started speaking, so we need to send an interruption frame, so it is traveling downstream, and we are interrupting the different processors based on this frame. Now in order to the flow, how this interruption frame gets traveled downstream is, we are gonna discuss more on that in the code towards the end. But I'm gonna just tell you that first, we the transport sends a uh, um, in interruption task frame to the pipeline task upstream, and then pipeline task sends an interruption frame downstream. So transport send it and task frame upstream, and interruption frame is received. When this transport received, then it sends to all the different processor. So this is how the interruption works, and we have two types of interruption. So interruption frame is always downstream, but task frame is like upstream. So all the different, we will be going to see different types of task frame. All of them are upstream, and they trigger some other frame, and that frame is always downstream. So we have to keep this in mind, and I'm just gonna go through this. So transport detects user is speaking, and they call this method push interruption task frame, and it does a bunch of things which we are gonna see later. But basically it sends a interruption task frame to the pipeline task, and then once pipeline task creates this interruption frame, it sends it downstream, and then each processor receives and cancel the task and drains the queue and recreates a processing task. So this is something we are going to discuss more in detail towards the end. I'm gonna skip the code for now, but we are gonna come to the code towards the end. Yeah, so now coming to user speaking frames. So this is a kind of like a simple. We have these two: user started speaking frame and user stopped speaking frame. These are of system frame, and basically, as the name suggests, user turn has started, user turn has ended, and these frames are typically broadcast, like sent in both the direction, and it is generally emitted by LLM based on WAD STT events and some STT services also do it. And they are used by LLM when to generate the response and show speaker indicator and track conversation runs, like whenever we need to see, okay, some turn taking is taking place. So at that time we can use those. um, so how now there is something WAD user started speaking frame and WAD user stopped, which is different from user started speaking frame and user stopped speaking frame. um, Now, as the theme suggests, like a WAD and turn analyzer or turn manager, they take care of two different things. Like decides uh, whether the user has started speaking or not, or user has stopped speaking or not. So that's why it emits two different frames, which is related to WAD. And then turn manager decides the turn, like okay, this is now user has started and user has stopped, like that. So that's why we have these two different frames by two different sorry, we have four different frames, where the user started speaking frame and then user started speaking frame, where user stopped and where normal user stopped speaking frame. So I hope this is clear. So as I told, where the answers is sound present and user from answer who owns the term. So yeah. Now coming to bot speaking frame. So this is, as the name suggests, like bot started speaking and bot stopped speaking, out of which only the first and last is the system frame, because they are the higher priority. Like we would want to know, okay, bot has started, okay, bot has stopped. That helps us in turn taking or do other things. Bot speaking frame is not okay, this is also high priority, sorry, I missed it. So bot speaking frame is also of high priority, because it's periodic heartbeat, like okay, bot is currently speaking. And it is emitted by output transport when audio is actually playing. So all three are of system frame, and purpose is um, to know like interruption timing, know when bot can be interrupted, make changes to the UI state, like UI and timing depend on these frames, and they reflect reality and not intention. So now we also have something called as function calling frames. So the LLM, let's say LLM wants to make some function calls. So we have those different type of function frame over here, and out of which not everyone is a system frame. So function call started and function call cancel are system frame, and these two are not. Function call in progress is kind of control frame, and call result is data frame, because it carries the data, the result of that call. So as you can see in this example, so LLM is calling is making a call to some handler. So we have this function call started frame, and then call in progress, then some API call is happening, response, and then function call result frame. So if the user interrupts, then function call cancel frame. So, and we do the cleanup. So this is about the function calling frames. Now task control frame. Okay, so task frame is something that I've already explained during interruption. So when I talked a bit about interruption over here, um, so interruption task frame is something that we send it as soon as user starts speaking. So we send it to pipeline task, and then we receive interruption frame downstream. So task frame, we have different types of task frame. So we have end task frame, cancel task frame, stop task frame, and interruption task frame. So all of these are different task frame, four types of task frame, and they all travel upstream. And except for stop task frame, all of these task frame emit something downstream. So end task frame triggers end frame downstream, cancel task frame triggers cancel frame downstream, interruption task frame, as I explained, they trigger interruption frame downstream. So all of them triggers some frame downstream, and if you just remove the task, that is the frame that gets triggered, and it is traveling downstream. uh, yeah. So these are the different task frame, and I wanted to take a moment and discuss about end task frame versus end frame versus cancel frame. So end task frame is a system frame, and cancel frame is also a system frame, but end frame is a control frame. So task frame is usually upstream, and these two are downstream. And now uh, I wanted to uh, also help you understand how end frame works. Like if you remember, I was talking about the pipeline instance. So let's say we have multiple instance of pipeline. So like we have a different pipeline task running. So if end task frame is triggered, so this is something we are canceling the task. So one pipeline task gets cancelled, it does not affect the other pipeline task. But if end frame is received, then we are canceling that pipeline instance, that we are cleaning up all the processes and everything, because now it's kind of like we are canceling everything related to that instance. So so that's why mostly end frame you won't be seeing. You will only be seeing when we are closing the pipeline instance, and otherwise you will be mostly seeing end task frame. And then we have this transport control frames. So we have different types of transport control frames, like input transport, output transport, and output transport. We have two: message frame and message urgent frame. So out of which the first and third are the system frame, like input transport message and output transport message. So now uh, the objective is like these frames bridge the outside world. Input frames bring events in, and output frame sends messages out. So these are like urgent versions of bypass queues, and this is how UI and clients stay responsive. So external events arrived, and we are sending message to transport. And if there is any urgent message or something that we want to send, some emergency signal, so that's why this is a system frame, and this is just a data frame because it is carrying the data like message. uh, Process control frame is something that you should also know about. So processor control is something when we want to stop just one processor. So how can you do that? Like maybe for some safety purpose or something, we can emit those frames. So we have process frame processor pause and resume. So based on these, we pause, and once if pause is received, then we stop processing, and if it resume is received, we resume. So sometimes you might want to do it. We can get fine gain control without global chaos. So this is often used for safety or moderation. And then coming to uh, complete frame flow example. So these were the different frames that we have discussed. Now uh, I wanted to just give you a summary. what what are the different frames we generally deal with on a day-to-day basis. So generally, like when we are initializing, we send a start frame to each and every processor. Then we have this, whenever the user is speaking, we have this input audio raw frame received, and then STT converts that to transcription frame and LLM context frame. So this is something that we have not discussed, but you can see like audio is converted to transcription and then LLM context. So yeah, and then pod response. So we get this LLM full response start frame, LLM text frame, and then we are converted into TTS and all of that. So now user interruption, we have discussed briefly, but I'm gonna cover more in detail. So when the user starts speaking in between, we first send an interruption task frame to pipeline task, and then interruption frame is received, and then we send it to the transporter to STT aggregator and all of that to cancel all the different task generation output involved. So uh, mental model, every event becomes a frame. We have different downstream and upstream control flows. And priority, we have system frame, then we have data frame and control frame. So system frame is higher priority broadcast, both direction. We send event in both direction, upward, upstream and downstream. We have uninterruptible frame, which survive the crashes, like during interruption. These frames are preserved, and each session has its own frame flow. So pipeline task, yeah. So this is a quick table where you can see what are the different frames involved. System frame are usually high priority, like so all the system frame are high, and the others are low. You can see the type, and direction is downstream. So you can see generally the error frame, like fatal error frame is upstream, and task frame were upstream, like these two tasks you can see. So whatever task frame, they are upstream, and error frame otherwise mostly they are downstream. And there are certain frames which moves in both direction, so broadcast, like upstream and downstream both. Now some mistakes to avoid, like confusing priority with direction, like uh, priority high low is not equals to direction, and thinking end frame is a system frame, end frame is a control frame with low priority, and forgetting uninterruptible frame, like critical frames, like a function called result frame must survive interruptions, and thinking broadcast send to all processors. So basically they send in both the direction. So not every processor is sent at once, and not handling start frame. So this is something that you need to keep in mind. Then this is some hierarchy, you can go through it later on. I will be mentioning this MD file in the description. Now coming to the interruption flow in detail, I wanted to discuss this, and I'm gonna directly come to the diagram first, and then talk about the different pieces involved. So just a point to be noted, pipeline task in other diagrams I've kept it on the left. Here I've kind of kept it on the right, but you can keep it on the left. It's kind of like I just wanted to show that there is some pipeline task, and this was somehow breaking my flow if I kept it on left. So I've kept it on right, but doesn't matter. So we have different pieces involved, like WAD, transport, STT, LLM, and TTS. So if bot is speaking and user interrupts, so what happens? So WAD detects user speech, then WAD emits this frame, like WAD user started speaking frame. Now transport, it calls one method which is push interruption task frame and wait. Now we'll come to it, but I already told you what it does is, like whenever we get to know, transport sends a interruption task frame upstream to pipeline task, and then processor interruption task frame, we process interruption task frame, and it is sent downstream. Then once transport receives that, we are gonna send interruption frame to STT, LLM, TTS, and all of that. So you can see now there are some in between steps that we are doing. So what is that? When we call this method, we are doing three things. Now what we are doing is we are setting this wait for interruption flag. Sorry, let it load. Yeah, we are setting this to true, and we are sending one task which is interruption task frame upstream, and we are waiting till we receive the interruption frame. So uh, transport sends the upstream task, and it also waits to receive this interruption frame task so that it can send it to the other processors. So this everything is done in this method, push interruption task frame and wait. And then once we receive this event, we do the cleanup. Now how do we know that we have received this interruption frame, this interruption frame from pipeline task? How does this transport know? It gets to know using this push frame method. And in this push frame we have this we check whether we have received it or not, like if the processor is waiting and for interruption and we are pushing it, like we have received it, then we set this event, and once we set it, this wait is over, and we clean up the process. So it is kind of like a once this event is set, it is resumed from here, and we clean up. So like we set it to true, create a task frame, it is sent upstream, and then we are waiting. We are waiting at this is kind of blocked over here. And once this is received, uh, we it is received in the push frame, we are waiting, and we set this, and we are unblocking this waiting code. So when this is unblocked, we then send the interruption frame downstream, and transport can now process new input, so it can take the audio and everything, and then it can process. So now once we send that downstream, what actually happens is this STT, it's gonna cancel all the tasks. What all tasks? Like it's gonna start the interruption, it cancel the process frame task, it's gonna drain the queue except for the uninterruptible frames, and then recreate the process frame task. So similarly, LLM is gonna cancel the generation, drain the queue, then TTS is also gonna cancel audio generation, all of that. Now this is the whole flow that I explained right now. Now I wanted to take a moment to also talk about like why this is sufficient, because frame processing is sequential. Like every processor processes frame in order, and once transport pushes the interruption frame to STT, it is guaranteed that STT will process it before any new frames comes from transport. So new input will wait, like any new input, new audio from the user will be processed after interruption, because it will be queued after the interruption frame in each processor's queue. So we are first sending the interruption frame, and then we are sending whatever audio data that we had. And this cleanup is done asynchronously, as interruption frame flows through the pipeline. So this is the details of how interruption works, and let's go towards the top and see what we have covered. So we have covered what are the different what exactly is a frame, and why we are studying frame, and then why frames are essentials, the processor and the pipeline, like how the processors are linked, and what are the different pipeline involved, like what is the difference between pipeline instance, and pipeline task. Like this is a analogy that we have created, and why task matter, like what is pipeline task and why pipeline task matter. Task We have discussed the hierarchy of a frame, like a system frame, data frame, control frame, and what are the different kind of frame. So what is the direction, like upstream, downstream, and broadcast, like broadcast we are sending in both the direction. And then coming to the queue, we have two types of queue inside a processor: queue frame and input queue and process queue. And system frame are processed, they have a higher since they have a higher priority, we process them immediately. Rest all the frames are put into the process queue. So all the frames come in input queue, but this input task handler process the system frame immediately, and the rest of the frames are put in process queue. Then we discussed about uninterruptible frame. What are the different uninterruptible frame? Then we saw different system frames, like start frame, by what is the use of start frame, and it travels downstream. Then why it must be first. It carries all the different configuration that a different processor can set, and only after that data will flow. And then we have different error frame, like error frame and fatal error frame. It travels upstream. So only two types of frame travel upstream: one is error frame, and then there is task frame. For recoverable error we use error frame, for unrecoverable we use fatal error frame, so that each processor can handle forward. Now, interruption flow we already discussed in detail. Whenever user starts speaking in between, we transport sends interruption task frame upstream, and then interruption frame is received downstream. And then we also discussed in detail about the waiting mechanism and everything, and how each processor clears once they receive the interruption frame, and why this design is a good design, because we are not blocking this until each and everything is interruption free. Like have received the interruption frame and clear everything. As and when interruption frame is received, each of them can process, so that other processors are not blocked. We have discussed all of that. We have also discussed the code, and user speaking frames. So this is two user speaking frames, and then how we have bad user speaking frames as well, started and stopping speaking frame. Then bot speaking frame, to know whether the bot is speaking, bot stopped, and bot started. So these are the different three different system frame. And then we also discussed about the function calling frames. So LLM, if they want to call certain functions, so we have different function frame for that. And cancel and started is the system frame rest to our control or data frame. Then we discussed task control frame, like a task travels upward to the pipeline task, and then they trigger uh, other frame, like end task trigger end frame, cancel task cancel frame, interruption task interruption frame. And these triggered frames are downstream, but these task frames are upstream, traveling to pipeline task. Then difference between end task frame, end frame, and cancel frame. End task frame is system frame, end frame is control frame, and we have this cancel frame. Uh, Cancel is immediate stop, and is we are requesting graceful end. And transport control frames is also something we discussed, for transporting the message from somewhere outside, or somewhere from somewhere else we want to bring in the message. So custom events from client, send data to client or something else. Then processor control frames, sometimes you want to stop, like pause or resume a processor for some time or do something, then we can use these frames. And we also discussed the example. So that's it for today. Thank you for coming to my channel. And yeah, do like and subscribe the video if you find it useful. Thank you.